Hi, sir.
Hi, Abby. How are you doing?
I'm good. How are you?
Good, good.
That's good.
So, how is it going? We started with the calculus lessons and we are almost midway now. How do you find these lessons and how useful are they for you?
Oh, like 100% useful. It's like, yeah, really good. I think from the beginning, I found it quite tricky because just jumping into this big thing, and then you were sure that I was going to get it and find it easier, and which I am now. It's getting to the point where it's okay. It's good. Yeah, I'm understanding it better, so that's good.
Yes, yeah.
And I can do
Yes,
most questions in my book.
that's great. That's great. So, actually, it's a very important juncture. We have actually learned all the concepts of finding the derivative. So, calculus 1 basically is to find the derivative of the function so that we know. Now we learn the techniques of applying this finding derivatives in different ways. Now, for you, finding derivatives really means gradient, right? Whenever you see gradient of a function, it means the first derivative. Now,
Hmm.
with the help of first derivative, we could actually analyze a graph. We could see where the function is increasing. If the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. If the derivative is zero, gradient is zero. In that case, it is neither decreasing nor increasing. We call them as stationary points also, right? Because the gradient is stationary. It is neither increasing nor decreasing. Now, at these stationary points, you could have a maximum or minimum value. Most of the time, we say local maximum or local minimum value. Reason being very simple, since you know that polynomials or degree polynomials may go from negative infinity to positive infinity, right? So they don't really have absolute maximum or absolute minimum value. So in general, we say local maximum, minimum, but even if we do not say local maximum, minimum, we mean that, right? So
All
because
right.
in between all maximum, minimum points. So the word local helps us to understand it better that if we have a turning point, we have to analyze in the vicinity of this particular turning point about the gradient, how the gradient changes. If the gradient changes from increasing to decreasing, that means it increased to maximum, you reach the maximum, now you're coming down. So you reached up the hill and now you're coming down. So look at like this, that will help you to understand this particular concept. So if you
Mm.
look at the hill, you will also see it is like concave down, correct? So any graph which is concave down, if you're on the top of that hill, you have reached maximum. On the other side, it is the valley, right? So if you go down
Yes.
and then up, you have reached the bare minimum, right? So at maximum and minimum, the gradient changes, and it is actually zero at that particular point. So that is our focus for today. So we'll see how to identify the local maximum and minimum for a particular function. And later, we are going to do so many applications based on this. For example, optimization. Optimization basically is what? Maximizing your profits, right? Minimizing the cost. Think like that. So many applications where we have to do designing and get the best value. In that case, this
Oh.
particular concept is going to help you a lot. Perfect.
I was just
Easy.
thinking of a concept. Sorry to interrupt, but
Yeah,
in science, when we learn about like optimum pH levels and things, it's
correct.
like,
Yes, those
uh,
normal type of graph which you see, right? So
yeah.
that normal type of graph hits the maximum, then comes down. Perfect. So many, and even when you are moving up, at what rate are you moving up? That is also very important. The value of gradient tells you that what rate. So gradient also gives you increasing interval, decreasing interval, rate of increase, rate of decrease, so many parameters. And that will bring us to the next chapter, which is rate of change. So we are going to now, after understanding maximum, minimum, understand rate of change. And when we talk about rate of change, you know the three terms, displacement, velocity, and acceleration, they're all related with rate of change. So we'll have a chapter on displacement, velocity, and acceleration. So now basically you have understood the major concepts and the calculus has opened up a wide avenue for you to explore. So this is right time to explore many different applications. We'll begin with a maximum minimum. And while we are discussing that, lay emphasis on other things also, like rate of change, I said, right? So
Yeah.
because all of this comes together when we talk about calculus. Perfect.
All right.
So
Okay.
let me share with you today's screen, and then we'll see how to go about this particular topic, which is one of the most important topics in calculus. So Amy, today we'll learn about the application of derivatives. And as I was saying, when we talk about application, the foremost is what happens to the graph when it reaches a maximum, how to identify when the graph reaches the maximum, and trace that value, correct?
Mm.
So we'll talk about the application of derivatives. We'll begin with understanding what is a local maximum or a minimum point. We'll also look into the definition of stationary point and the critical points. Remember, these two are very different things, but they are normally mixed up. And so students get an idea that they're kind of exactly the same. And they do a huge mistake when, and they realize only when in examination, the very first question is, what is the difference between critical point and stationary point?
Oh,
that's
yeah.
yeah, then they realize, well, are they different? Come on. So we'll actually begin from here. So, and then we'll analyze the gradient with the interval table. We actually did kind of interval table when we were doing inequalities in functions, right? When you have to
Oh,
find,
yeah.
right? You remember that part? So we'll
Yeah, like
actually,
in between two numbers, and you choose a value, and then.
correct. So when you get your zeros, every zero, like if you have three zeros, zeros will divide your plane into n plus 1 regions. 3 will divide into 4 regions. We have to see each region, where is it positive or negative. That is the
Yes.
interval table. We'll again visit it. Then we'll sketch the graph for polynomials. Earlier also we did the sketch, but we did it without identifying the maximum and minimum points. What kind of a rough sketch we gave. This time we cannot actually call it a graph of a polynomial function rather than just sketch a curve. We'll also see how to sketch graph from a gradient. So there will be examples where I will give you the gradients graph and I'll tell you, well, now do the reverse calculations and give me the graph of the function itself. We'll have examples to find local maximum minimum, and then we'll have examination style practice test paper. Now, this topic is so important that in every exam whatsoever, whether it is GCSE, AP Calculus, or in Canada, or in Australia, or in India, or any part of the world, there will be questions based on what we are going to learn today. So the examination types test paper, I just picked up three very beautiful questions, and I'm sure along with the examples which I've taken up, those will help you solve most of the examination type test papers, right? So let's begin with a very simple concept on maximum. So here is a parabola which we have been seeing right from the very beginning of functions. This is turned upside down, opening downwards. Definitely, we have a maximum, right?
Mm.
This graph has a peak at 4, and that is a function which you're familiar with. F of x is equals to minus x squared, so opening down, plus 4. That is your y-intercept, right? Now,
Yeah.
if you find the gradient of this function, the gradient of this function is minus 2x, right? Now, minus 2x will be 0 when? It will be 0 at 0, correct?
Yeah.
Minus 2x will be 0 at 0. If I give a positive value, I'll get a negative value of the gradient, correct?
Mm-hmm.
Because minus. But if I give a negative value to x, it will be positive value. So the gradient graph will look something like I've shown here. Is that clear to you?
What, the highlighted yellow? Oh, okay. Yeah.
So that is the gradient graph, which is f dash x, correct? So what you notice on this graph is that this side here is 0, which corresponds to maximum, correct? On the gradient. On this side, it is positive. And you can see that your tangent is positive on this side, correct? Rising up. On the
Yeah.
left side of your maximum, your tangent is positive. And on the right side, if you draw a tangent on any part of the graph, it is coming downwards. It has a negative value, which is represented by the graph, which is below the x-axis, correct?
So is that line that you've drawn the graph of the gradient?
Yes, minus 2x.
Oh, okay. Yeah.
Clear? So you can see very easily now a simple parabola function, which is degree 2. Its gradient will be degree 1 degree less. It's a straight line with a slope of -2. Perfect. And you
Yeah.
notice that at 0, 0 corresponds to the maximum. Perfect. And you can see while you're approaching the maximum, the gradient is increasing, positive rate of change.
Yeah.
And the gradient decreases after the maximum. So when the gradient changes from increasing to decreasing, it hits the maximum.
Uh,
And at maximum, we call that point is a stationary point because the gradient is not changing, it is 0.
no. Oh,
So
right.
that's how
Okay.
all these terms are related. Perfect. So now let's go
Sense.
through what I have written here. These are very critical points. So I've clearly mentioned each and everything absolutely clearly. So, Amy, I would like you to read from here onwards.
So, gradient is 0 at the maximum.
Mm-hmm.
Gradient is positive on the left of the maximum.
Correct?
Gradient is negative on the right of the zeros. And maximum is a turning point.
Yes. So the maximum of the gradient is the turning point, right? Now that brings us to a very important definition, and that is the definition of a critical point. Critical points on the graph of a function are the points where the derivative or gradient is 0 or it does not exist. So that is how we define a critical point. Critical point could have a derivative which is 0 or it does not exist. Now we should understand that critical point is a very different word than the stationary point. It could be 0. If it is 0, it may be called as a stationary point. Okay,
Yeah.
because it is 0. However, if it does not exist, then it is not an stationary point.
Oh, okay.
But when it does not exist, we could have local maximum or minimum, as you see in absolute function. The vertex of the absolute function, there you have a minimum, but the derivative does not exist at that point. So it is a critical point, right? Because it
Yeah.
tells you exactly that there has to be or there may be a maximum or a minimum, right? And we
Yeah.
know at that point the gradient is not 0. So it is not a stationary point. At a stationary point, the gradient should be 0. Okay, so that is the difference between stationary point and the critical points, correct? So at these critical points, we may have a local maxima or a local minimum. Now, important thing is we may have, not necessarily. Okay, so
Oh,
if the gradient is 0, it doesn't necessarily means that there will be a maximum or minimum. Could you give me some examples on that?
where there is no maximum or minimum.
But derivative is 0.
The cubic function, where
Perfect.
there's a saddle point.
Yes, so that saddle point is a critical point. It tells you a lot about the curve, and therefore it is called a critical point. However, we don't have a maximum or a minimum at that point, right? So
Yeah.
again, we have a 0 there, but not a maximum minimum. So the only difference between that point and the maximum minimum point is, we'll learn later, that the concavity changes. One. Second, we see that the gradient actually doesn't change from positive to negative. In a cubic function, you will see, I've taken up an example, that it is going up and then again up. It doesn't go down the graph of the gradient. Do you see that?
Yeah.
So
Because if
for,
you draw lines, they're
yes,
parallel, go up.
they go up and up. They don't go up and down. So the tangents at these points do not go from increasing to decreasing or from decreasing to increasing. And therefore, we do not have a maximum or a minimum at this particular point. It may be referred to as saddle point, as you said, or point of inflection, we'll soon call it. Is that okay?
Okay. Yeah.
There are 3 basic points which we normally work with. Critical points include the other 2, which are stationary and saddle points. Okay? Now, let's elaborate on this particular simple example to understand the concepts which are going to help us understand this particular unit fairly well. So as I was saying, Amy, we have the derivative of the function as minus 2x. We just found that the critical point here is at x equals to 0. For that, substitute f dash x as 0, right? So I'm writing on the right-hand side, to find a critical point, equate derivative to 0, right? And find the value of x. So when I equate minus 2x to 0, I get the value of x as 0. In this particular case, I have only one critical point. Now, this critical point, x equals to 0, divides our plane into two parts, right? Left side of 0 and the right side of 0. Simple as that. So that is my x equals to 0. The two parts are left side and right side. I'm actually utilizing the knowledge which we actually learned about the interval tables to figure out where is the gradient positive and where is the gradient negative. Strictly speaking, we are not interested in the value of the gradient. We are only interested in figuring out whether it is positive or negative. Perfect. So take a test point. On the left side of 0, we have to be close. I've taken minus 0.1. On the right side, plus 0.1. When I substitute this value in our gradient function minus 2x, right? Minus minus gives me positive value. But when you multiply with negative 2x, you get a negative value. Positive gradient means the graph is increasing, as you can see from here on the left side, and on the right side, the graph is decreasing because the gradient is negative. Since it changes from increasing to decreasing, we have a maximum at x equals to 0. Is that clear to you?
Yeah.
So that is kind of very important to understand, right? So this critical point where the gradient equals to 0 is also called a stationary point, right? Since it is 0.
Yeah.
Gradient is 0 implies function is neither increasing nor decreasing at that particular point, right? So it is 0. That's what it implies, and we call it a stationary point. Now, here is a question for you, Amy. Can you read the question and answer this particular question?
So, are all critical points stationary points?
Yes. What is the answer?
Wait, are all critical points stationary points? No.
No, that's correct. Because in critical points, you're also looking into?
Does not exist.
Does not exist.
Okay.
Now let's analyze the graph where the parabola is opening upwards. We kind of flipped it. And this time, as you know, the function is f of x equals to x squared minus 4. So as you know, now parabola has the minimum value at minus 4, correct? X equals to 0, the minimum value is minus 4, correct? Now again, going to the principles of our gradient, what we understand. If we move from the left side, the gradient is negative, right? And then on the right side, it is positive. Gradient changes from negative to positive. So at the critical point, it should be a minimum. That is what it is. Right? So, Amy, can you once again go through what I've written here?
Gradient is 0 at the minimum.
Yes.
Gradient is negative on the left of the maximum.
Yes.
Gradient is positive on right of zeros. And minimum is a turning point.
Perfect. Now we will analyze this particular gradient at a point very close to the critical point. Very close means x equals to 0 is our critical point. We'll take a point on the left side, which is x equals to minus 1. On the right side, x equals to minus 0.1. Okay, 0.1, right? Well, you could take minus 1 and plus 1 also. You could do that because here we have only two intervals. So any point could do. Closer it is, better for us. And remember, we are not interested in calculating the values. We are only interested in finding whether the gradient f dash x, f prime x is negative or positive. Perfect. So we got our equation for the gradient, which is f prime x is 2x. When I substitute a negative value, it becomes negative. When I substitute a positive value, it is positive. So what we see from the left side, it is decreasing. On the right side, it is increasing. So it's a minimum at the critical point. Is that clear to you?
Yeah.
Now the question is, what is the value? To find the value, just substitute 0 in the f of x. So you get minus 4. So minus 4 is your minimum value. So in the previous example, you could have substituted, find f of 0. You would have got plus 4 as your maximum point, correct? So at x equals to 0, we have a minimum value of minus 4 in this particular case. That brings us to another question, which is question number 2a and 2b. So Amy, can you just go through these questions and answer them?
Yeah. So find the critical points on the graph of f of x equals x cubed plus 1. So would you just find the derivative of that
Yes,
function?
correct.
So
And equate it to 0.
yeah, so that
What
would
is
be
the
3x
derivative?
squared.
Yeah, tell me, what is the derivative of x cubed?
3x squared
Perfect. When will it be 0?
at x equals to 0.
Perfect. And at x equals to 0, it is 3x squared. That means if you take a point negative or positive, x squared will make it positive. So it is positive and positive. And therefore, the gradient is not changing its sign, right?
Yeah.
And therefore, we don't have either a maximum or a minimum at this particular point, correct?
Yeah.
Now, I'd like you to read question number 2p and answer that particular question.
Explain why the critical point found above is not a stationary point.
Yes. I should have written is not a maximum or a minimum.
Oh, okay.
Okay. Yeah. So, yeah, that is a correction which I'll make. Okay. So it's not a maximum or a minimum. Okay. Now, let's move on further and take the next example, which is a cubic function. Example number 1. Analyze stationary point for local extrema. When I say local extrema, I mean to say local maximum or a local minimum, or at different points we could have different things.
Mm.
Find the stationary points on the graph of f of x equals to x cubed plus 3x 6x squared minus 32, and then sketch the curve of f of x. Perfect. So that's the question for you. It's a very lengthy question, and it's taken from a kind of exam in previous test papers. Now, what should you do? The steps to be followed are: you begin by finding the critical points, correct? For a polynomial, as you understand, you have derivative at each and every point. So every critical point is also a stationary point, correct? So for polynomials, we can just use the term stationary points, okay?
Right.
So, but I prefer to use critical number. The critical number or a critical point is kind of same thing for me. When I say critical number, I'm only interested in the value of x. But when I
Oh,
say point, we want both x and y coordinates. So
right.
sometimes it could have a difference. So the number is the number x, and analyze the maximum minimum. So first step will be, starting with the function, we'll find the derivative of the function, which is given right there. To find 0, because stationary point means that the derivative is 0, is good practice to factor. As soon as you factor, you now know 3x times x plus 4 is the factor, which can be 0 only for x equals to 0 or x equals to minus 4. Correct? So these are two critical numbers, or you can say stationary points, in our example. Now, to find whether we have a maximum or a minimum at these points, we are going to analyze the situation using an interval table, correct? So we have two critical points which are at x equals to minus 4 and 0. So these two divide our plane into three regions. In each region, I'm going to take a test point. So test point is minus 4, which is to the left of minus 5, which is left of minus 4. And then I've taken a test point minus 1, which is in between minus 4 and 0. And on the right side of 0, I've taken x equals to 1. So these are my three test points. You can plug in the value of these three one by one into your function and see whether you get end result as the positive or negative. But what I prefer is split the function into its factors. So we have two factors. One is 3x, the other one is x plus 4. For each point, if it is minus 5, we know this will be negative, minus 1 will give me negative, plus will give me positive. So for 3x individually, we found the sign. Similarly, for the other factor, which is x plus 4, we find that the signs are negative, positive, and positive. Correct? If I substitute minus 1 plus 4 is positive. If I substitute minus 5 plus 4 is negative. Now, the function is product of both of them, correct? When you multiply two negatives, you get a positive. When you multiply positive and negative, you get a negative. When you multiply two positive, you get another positive. Now, this is important that you split it into factors and then do it, because in test paper, calculator may not be allowed for this particular test. So be open for that. And in calculus, you could have two test papers, one without a calculator, and whatever we have done so far is all without calculator. Okay. So calculator will not be allowed for this particular test paper. So once you split, it's easy calculations. You can do it mentally very fast. Since it is positive gradient, we know it is increasing. Negative means decreasing, then again increasing. It clearly indicates that we have a maximum at x equals to -4 and minimum at x equals to 0. Is that clear to you?
Yeah.
So till now, we have figured out our critical points, and we have also associated maximum and minimum points to them. Now, to find the value, so we know maximum is at -4 and minimum is at 0, correct? Now, to find the value, just plug in the value in your function, the equation given to us, correct? So when you write this value here in the function itself, you do your calculations at -4, you get this as 0. So the maximum is at -40. You get a point on the graph of the function which represents the maximum value. Do you see that?
Oh.
For f equals to 0, when you plug it in, you get minimum at 0 -32. So you have the minimum value of the function, also local minimum, which is 0 -32. Correct?
Mm.
Now, we have to sketch the graph of a polynomial, which is a cubic function. We'll have to review what we learned in polynomials. So with added information of maximum minimum point, we have to begin all over again. To sketch the graph of a polynomial, we look at the leading coefficient. Leading coefficient is positive. It's a cubic function. That means it is going to go from quadrant number 3 to 1. Always into, you see that? 3 to 1.
Yeah.
Cross like this. But do you notice, did we get any 0 in this particular case so far?
No.
Yes, -40. So that maximum value happens to be at a 0. So for this cubic function, we fortunately, while working on maximum minimum, we did get a 0. So we can use that 0. Otherwise, we'll use the techniques learned using the factor theorem to factor this particular polynomial. Perfect. Now, since we know that at -4, we have a 0, we'll divide by -4 to factorize the cubic equation, correct?
Yeah.
So I've used the synthetic division method. We have something missing here. Do you see that? The x value is missing. So I'm replacing this with a placeholder 0. Recall that, correct?
Yeah.
Writing the coefficients 1, 6, 0, and -32, dividing by -4. You can also do long division to get this, right? Oh, synthetic is faster. Bring down 1, multiply by -4x, add them, right? So when you add them, you get +2. Continue with this process. As expected, remainder is 0 since x plus 4 is a factor. But that gives you the quadratic equation, which is the another factor. So you can write the function as x plus 4 times x squared plus 2x minus 8. Is that correct, Amy?
Yeah.
You can recall that, correct?
Yeah.
Now, the later half of the factor is simple quadratic equation, which using product and sum, you can now factor. So -8 means 4 times 2. 4 positive, 2 negative will give me the coefficient of x, which is 2. And therefore, I could write this as x plus 4 times x plus 4 times x minus 2. That means x plus 4 whole square. We have a double root at -4 and a single linear 0 at x equals to -2. Correct?
Mm.
So we have completely factored our polynomial. This is a cubic function. We know the zeros and their properties, the order or multiplicity. We know our maximum minimum. Can you sketch the graph now?
Yeah.
Perfect. So I'll give you more practice questions here. Let's look at the graph of this particular function, which is right there. So let us put all the information which we have gathered so far. We worked with this polynomial cubic function x cubed plus 6x squared minus 32, whose derivative we found could be written as 3x times x plus 4, giving us two critical points, x equals to 0 and x equals to -4. And we also found local maximum at -40, minimum at 0 -32. So on a graph, we'll plot these two values. Correct? We also found that the local maximum was our 0, and that helped us to divide and find the quadratic factor and then factorize further. And when we did so, we wrote it in a factored form, which I should have copied, but not. But I've written the zeros. So we figured out that there are two zeros. One is at -4 with multiplicity of 2. Sometimes we say order of 2. The other one is a linear 0 at x equals to uh, 0, right? So uh, x equals, no, this linear 0 is at 2. I wrote the wrong value. Let's go back. So at x equals to 2, not 0, right? Do you remember this?
Yeah.
X equals to 2. So that is a type.
So it's like a line.
Yeah. So
Yeah.
let me just write down this as x equals to 2. Correct? Which is this particular point, right? Okay. So we have two zeros here, one at x equals to -4, which is right there. And the other one is right there. Is it clear to you?
Yeah.
Those are my two zeros. We also understand that this is a cubic function where when x approaches positive infinity, y approaches positive infinity. That is this end. When x approaches negative infinity, y approaches negative infinity, which is that end. Connecting the points, we know we have a turning point at this particular 0 since the multiplicity is 2, right?
Yeah.
So that gives the turning point. We go through the minimum value, come up and cross the graph at another 0, which is at x equals to 2. And there we go. We have very fairly accurate graph of a cubic function. Do you see that?
Yeah.
So this is what we are going to call a graph. What we had been doing earlier was sketch a polynomial. This question is graph a polynomial. Do you get the idea?
Oh, so graphing is literally accurate.
Yes. You could find 1 or 2 points here to add accuracy, but that is not required. This is more than enough. Okay, 5 points we have to give. We already have 5 points. We have maximum, minimum. We have zeros, the end behavior, correct?
Yeah.
So with that, we give 5 points. But for accuracy, you could find 1 or 2 values. Is that clear to you?
Yeah.
But only if time permits, but this is enough. Now, let's move on to the next part. Did you understand this process?
Yeah, makes a lot of sense now.
Okay.
So we can sketch any graph now, like any graph.
That is where you are now, correct? Explain me in short, how will you sketch a graph of a cubic function?
In short, okay. Right, so we start with the cubic function given. Then you do the, the derivative form of it. Yes. Find the critical points, that's the first step. Once you find the critical points, then you divide, like you do the interval table. Yes. And we can't use calculators for this one. So when we factor it and you get 3x and you do x plus 4, make them as two different like individual equations, sub the values in. You don't need to find accurate value, you just need to see if it's negative, positive, that's simple. Write down the signs, and because we're multiplying them, as you know, multiply two negatives, you get positive, positive and negative, you get negative, and both positive, you get positive. So once you know those final values, if it's positive, it means it's increasing. If it's negative, it's decreasing. That's quite simple. And then if it goes from increasing, if the concavity changes from increasing to decreasing, we get a maximum. And
give me a minute. Yeah. So you check the gradient or the derivative, whether it is positive, negative, or what. Now, if the gradient is positive, right? Don't talk about concavity now. Concavity we'll see later on. So if the gradient is positive, that means the function is increasing. If the gradient is negative, the function is decreasing. That means it has already hit the maximum at 0, right? So we have reached the maximum point. Yeah, continue from here, please.
That makes sense. Yeah. Okay, so then you hit the maximum and then you got your minimum values. Yeah. So once you find your minimum and maximum value, you just sub those values back into the original cubic equation, the f of x equation. Then you get the y values. Now you've got your actual points. So like we figured out, we got our local maximum at -4, 0, and local minimum at 0, -32.
Okay.
Once you have them, you should watch Mr. Kumar's videos on how to sketch a graph for starters, because this would maybe look a bit too confusing. But once you get that, all you do is you look at end behavior, you look at the leading coefficient, know from which quadrants it goes to. So in this case, it goes from 3 to 1. then we know you need to know your zeros, the multiplicities, the order of them, and once you figure all that out, so you go to the point, so at x equals -4, we know the order is 2, so that would be a curve, little quadratic, and at x equals 2, the degree is 1, so therefore it'll be a linear line. You just join all the points up, and you got your graph.
Perfect. That's great. Normally, in a test paper, you'll be given about 10 minutes to solve this question. So do not rush. Do accurate calculations, get your points, and make a smooth curve as I've shown here, right? That is very important to gain all the points here. This is not a question to rush, okay?
Okay.
Now, so when you read your test paper and you hit this question there, you should allocate this as 2 questions because it is going to take double the time. We have to find critical numbers analysis of that, and we have to also graph it, right? So it's basically 2 questions in one. So you have to give 10 minutes to this question in examination, okay?
Just wondering, how many marks is it?
Well, maybe 10 marks for you.
Really?
Yes.
Oh my
So
god.
look into some of your test papers and then you will come to know. But definitely they will have a polynomial and this kind of question, okay?
Wow, that's a lot of marks.
Yes, and in my practice test, you'll see some more questions which might take even longer, okay? So, so that's kind of interesting. So now we'll look into the different aspect of derivative. Question number 2A is to understand the graph of a derivative. Remember, we had been sketching graph of the derivative from the function till now. We were starting with the function and getting on to the derivative. This time, I've taken up an example where we are going to do the reverse, and that is to say, we'll begin with the derivative and end with the function. So that's kind of very critical. Now, Amy, this is a question for you. I will like you to read the question and answer.
Okay, right. So given the graph of, do you say f respect to derivative?
Prime, f prime x or derivative of x or gradient x, you can say. Gradient of f of x, yes.
Let's do f prime x.
Yes.
For what values of x does f of x have? So a local maximum. Wait, do I just read the questions then answer?
Yes, first, yeah, first you read the question. Yes, A.
Okay. A, so local maximum. B, local minimum.
That's it.
Okay.
We are given the graph of the derivative of the function f prime x. You need to find from this graph the value of x at which the function will have a local maximum or the function will have local minimum. Can you tell me the answer from the graph?
I feel like would it just be the 2 turning points that I can see, or is there a twist to it?
This is the graph of the derivative of the function.
I don't know how to switch it to the function.
Yeah. So it is a mindset. So we had been working so long with the functions. So as we are given a graph of the derivative of the function, we kind of get confused, and that's what exactly happened. Now, Amy, let's look into it with a fresh mind.
Okay.
What is the critical point?
Critical point.
Tell me, what is the critical point? Derivative equals 0. The stationary point or the critical point for you for a polynomial, we'll just say both, is what? Where the derivative f prime x is 0, correct?
Yeah.
So when you are analyzing the derivative graph, you have to look from the critical point. So you remember in the last example, when we started with the polynomial equation, we first found the derivative, and then after finding the derivative, we said these are our critical points, which we got after factoring. In this case, already the derivative is before you. In fact, the graph of derivative is before you. So now you will identify the critical points and you'll begin from there. And then analyze the critical points to find local maximum and local minimum. Do you get the idea?
Yeah.
Now tell me, what are the critical points from the graph of the derivative of the function f prime x?
So would it be x equals to 0.5 and x equals to 1.5?
So these values actually are 0, 1, and 2. Okay. So
Oh,
difficult to read from such a small graph, but yes. So these are the x-intercepts of the derivative of the function. So these are your critical points, these three. Correct?
oh yeah, it's not going to be the, sorry. Yeah, it's not going to be
Correct.
between those because it's the turning point.
Exact points where the graph crosses the x-axis, the zeros of your derivative of the function are the critical points.
Yeah.
So we have found the critical points. We have three critical points here, 0, 1, and 2. Definitely these critical points may represent local maximum or local minimum. Let's begin with the very first one, which is at 0. Is it a local maximum or a local minimum? Tell me.
Neither.
Why?
Because I don't know, the gradient's not changing.
This is the gradient. Gradient is negative here. This is the graph of gradient. This is negative here and positive there.
Oh, so it's changing. So if it's going from negative to positive,
Yes. Then it will be what?
then
Local?
minimum.
Correct. Correct. Such a difficult question, Amy. Do you see that?
It doesn't look like it though when you look at it like this, does it?
It's so difficult. So that is the very first application of derivatives, and see how confusing it is. The
Yeah.
chapter looks so simple to understand, but when it comes to real questions, it could be extremely confusing. And in the application section, that could be your first question. You get my point?
Yeah.
Many students come, oh, that was so simple. I just did this. And later on, they figure out it was all wrong.
Yeah. So clearly, it's not like logical reasoning.
No, it's logical reasoning, but clearly you're not looking at f derivative, right? You're looking at still the graph of a function. You see that?
Yeah.
So let me just get back to this from our table. So we have actually done the major part for you. That is, we have actually given you the derivative function, correct? Not only the function we have given, we have also told you how does it vary. So we have also included this part. On the left, what is happening on the derivative? See, this is derivative, right? F dash
Yeah.
s. Correct? We are saying that the derivative should be positive or negative. Now look at the graph once again. In the graph, we are saying this is derivative, and below axis, it is negative. Above the axis, it is positive. Correct? So at 0, it changes from negative to positive. Correct? The graph like looks going upwards, but strictly speaking, negative is the arrow pointing down.
Oh.
So negative is negative. This is negative, right? Arrow pointing down.
Yeah.
So you hit
It's
a minimum.
weird because like everything's given, right? Like the derivative graph is given and everything, and it's given everything, but I'm finding it really hard to just do this. It's like you said, it's the mindset changing now.
It's a mindset. So you have to really focus and then look at it here. So you say, if you don't really get it clearly, you very clearly write big and bold, this is graph of f prime x. Does it make sense to me? Yes.
Yeah.
So it is negative here and it's positive here, correct? Then it is negative here, and positive there, correct?
Yeah.
In this point, 0, it changes from negative to positive, like negative and then positive. This is gradient. Do you see that?
Yeah.
So we hit a minimum.
All right. Okay.
Correct?
So, yeah.
So we have a minimum at 0, and this point, it changes from max positive to negative, right? This
So that's maximum.
Yeah, it was going actually up. It shows downwards, but actually it's positive.
And the final one is also minimum. Yeah.
Now, I'd like you to now read. Second part is sketch the possible graph of f of x. So very difficult question. First thing you have to figure out positive or negative, the maximum, minimum. After that comes the question, which is sketch the graph of the function. Come on.
So you're killing me. What? Okay, I need to, because I'm in the mindset of doing the derivative, like sketching the derivative. Now I have to go back.
Yes, reverse thinking. It's all backwards, right? It looks
Okay.
different.
Yeah.
So it's like finding the inverse of a function, right? You go
Yeah.
backwards. It's kind of like that. Now, doesn't matter. We have gone through the hard step, and now it's easy thing. Read the solution for me if you understand that part.
Okay. So graph of f prime x indicates critical points at x equals 0, 1, and 2. So
Yes,
those are the points you highlighted. Yeah.
yes,
At x equals 0, f prime x changes from negative to positive,
yeah, negative.
resulting in a local max.
Minimum.
Um, oh, look, minimum, sorry.
Yes,
X equals 1, so f prime x changes from positive to negative, resulting in a local maximum. And x equals 2, f prime x changes from negative to positive, resulting in a local minimum.
is that clear?
Yeah.
Now look at the figure once again, the description once again. Try to put this capture this picture and then be simpler, okay?
Yeah.
Now, let's move on to the second part of this particular question, which says graph the derivative of the function, okay? Now let me give you some tips before we get into the graph. This is the graph given to us of the derivative. Now in polynomials, kind of very simple to understand that the derivative is 1 degree lower. Now we are given the derivative, we have to go to the function. Function will be 1 degree higher. Do you see that? Because
Oh.
the derivative was 1 degree lower. So this graph suggests us a cubic function. So we are looking for the function should be quartic, 4 degree, because the derivative is cubic, right?
Oh, yeah.
So we're looking for a quartic function. Quartic function, look at this graph. It is positive, right? Increasing, positive. Is that clear to you?
Wait,
Positive,
sorry,
right?
where are you highlighting?
Oh, sorry. In this portion of the graph, it is negative, right? Oh, sorry. Let me just change the color.
Yeah, sorry, there's lots of colors going on.
Yeah, let me just. Well, if I look at this part of the graph, the gradient is negative, right? Below
Yes.
x-axis. Gradient negative means the graph will be decreasing. So we have already sketched the graph. Let me explain you how we are getting it. So on the graph, we know gradient is negative, and we also have decided that the polynomial should be of degree 4 for the function. Is that clear to you?
Yeah.
So this is your degree 4, and see, the graph is coming downwards. That means gradient is negative. You understand? If I draw any tangent on this side, it will be downwards. So gradient is negative.
Oh.
Now we have a turning point, and this turning point matches with our 0. 0 on the derivative. Do you see that?
Yeah.
0 of the derivative is the turning point on the function. So if I sketch a function at the turning point, the derivative will be 0. The gradient, it's a stationary point. It's a local minimum in this particular case, which we decided. Yes, it is a local minimum. It all matches. Do you see that? This point is the local minimum on your red graph, which is that of a quartic function. Does make sense to you?
Why is the point like 2, 0 not a local minimum?
At 0, the gradient changes from negative to positive, right? So it is the local minimum. So see the graph, it turns at this point, red graph.
Oh,
So
so
that's a minimum.
the
Red,
red graph has 2 local minimums.
yeah, it has 2 local minimums.
Oh.
Got it?
Yeah.
The other one will be at this point. The yellow highlight is better for this. I would mess. Do you see that?
Yeah.
So we have 2 local minimums as we discussed. Perfect. So what we could do is, we have local minimums here, right? So we kind of have a turning point at these points because minimum maximums are turning points. And we have a local maximum there at this 0, right?
Yeah.
So you make a turning point, right? You make a turning point, correct?
Yeah.
So once you have this particular turning point, the graph has to turn from there. So we know these 3 turning points, right?
Yeah.
So, and second, we know that the graph actually moves from, because since it is a quartic function and it's moving from quadrant 2 to 1, so it is going to come down, negative gradient in the beginning, then positive gradient going up after the minimum. Correct?
Just a quick question.
Yes.
How did you know it was So how do we know it was a cubic?
Quartic.
Because the derivative, no, but the derivative is cubic.
Derivative is cubic. That means
So
the
it would be
function
1
should be
degree.
quartic, 1
Okay,
degree
1
higher.
degree. Yeah.
Because the rule is x to the power of n, derivative is n times x to the power of n minus 1.
Minus 1.
So the derivative is 1 degree lower. The function is 1 degree higher.
Oh, yeah,
The
yeah.
cubic 1 degree higher will be quartic, 4 degree. Is that clear to you?
Yeah.
Now, I'd like you to read the solution 2a, and then we'll get back to this particular graph once again.
So solution 2a, graph of f of x from f prime x. So f prime x being greater than 0 indicates f of x increasing.
Now wait. So we are saying that the derivative is greater than 0, which is this particular portion. Is that okay? Positive.
So,
In this
yeah.
particular portion, correct? So do you see in those particular portions, we have a positive gradient, correct?
Mm-hmm.
Increasing. The function is increasing. Do you see that function is increasing? And then again, the function is increasing. Do you see that part?
Yeah.
So that is how you have to see. When the derivative is positive, at that time, the graph of the function will be increasing as shown here.
Yeah,
Correct?
makes sense.
When the derivative is negative, function is decreasing. It is negative in these regions, correct? Negative? Correct? Decreasing and decreasing. Do you see that decreasing?
Oh, okay, yeah. Yeah.
It does make sense. And at turning points, you know, your local maximum or local minimum, which we already have. You wanted to have two minimums, which are here, two local minimums, correct? One maximum.
So, could I take a quick picture?
Sure.
Cool, thanks.
Now, I'd like you to read the solution once again, and then we'll go through this graph, and I'll point on this graph whatever you're reading, so that makes sense to many viewers who will be watching it later. Yes.
Okay.
Read the solution.
From the top?
Yes.
Oh, from there. Okay. F prime x being greater than 0 indicates f of x increasing.
Correct?
Yep. F prime x being less than 0 indicates f of x decreasing.
Yes.
F prime x equals 0 indicates f of x as a turning point.
Correct? 3 turning points. Look at the green graph. So those zeros are green graph zeros. Is that okay? So those 3 corresponds to turning points. Perfect?
Yeah.
Now, read the rest.
So maximum and minimum on graph of f prime x indicates point of inflection on the graph of f of x.
Yeah, because see on the graph of f prime x, you will see that we have these two. That is maximum, correct?
Yeah.
On the derivative has reached the maximum limit, right? So derivative has reached the maximum limit. It really means rate of change is maximum, correct?
Yeah.
So that rate of change, which is maximum, is showing here. So that maximum value, as this maximum value is corresponding to that value. Concavity is changing at this point. We call this point as a point of inflection. So you'll find that the region which we are looking at, it is positive. It is a gradient is positive. But rate of change of gradient initially from 0 to positive, so it has reached maximum point. Since now from positive, it is again reaching 0. Do you see that? Horizontal. So from horizontal to a maximum positive, from maximum positive to horizontal 0. It is positive all throughout, but that is the maximum value, which is represented by the maximum of your derivative. Do you see that?
Yeah.
Similarly, the minimum of the derivative gives you another point of inflection. So this particular point, let me just show you once again, will correspond to this point. Is it clear? So what has happened here? The gradient is negative. Of course, it is negative. It is coming down. However, from 0, it is coming down to negative. it is most negative here, since at the end it is again 0. So it must be rising from negative to 0. Do you see that part?
Yeah.
So it is rising. Do you see that?
Yeah.
That's negative. So at the maximum and minimum of the gradient, we get a point of inflection where the concavity is changing. Or you can say that at that point, the rate of change is maximum, whether it is towards the positive side or towards the negative side. Does it make sense?
All right.
We'll
Yeah.
actually work more on this in coming lessons when we talk about second derivatives and point of inflection. Okay?
Okay.
Continue.
Right. So graph of f of x will be quartic, will be a quartic function since the derivative is a cubic function.
Correct.
So that's when you said we do the n and then x times n to the minus 1. So we have to add 1. That makes sense. And then from the above observations, the graph of f of x can be sketched as shown.
Perfect. So you have to bring everything together to sketch this particular graph. It is definitely not an easy exercise. And it only comes from a lot of practice. So you know how much work is to be done now, right?
Yeah. I just need to remember stuff like, just generally sketching the polynomials. I'm just going to quickly go back to them because I feel like I'm missing a few things.
Correct.
Like, the order and multiplicity and that. Yeah.
Perfect. Perfect. So you just review that and then
Yeah.
we'll continue with this. Now, here is another very interesting example. Now, I've taken this example mainly because I want to differentiate between the stationary points and the critical numbers or critical points. As I was mentioning, the critical point, I've also written the definition here, is critical points on a graph of a function are the points where the derivative is 0 or it does not exist, right? So it could be 0 or does not exist. At stationary point, it should be only 0, right? So at these critical points, we may have a local maximum or local minimum, right? The question is we may have, correct? So now, explaining this concept, I've taken a radical function. So it's a composite function. The question here is, identify local maximum and minimum points of the function with the values. The question is, find the values of x for f of x equals to x squared times cube root of 6x squared minus 7, right? We'll have local maximum or minimum. Now, Amy, this first part is very clear. You need to use the product rule and find the derivative, correct?
Right.
So we can actually apply the product rule to the given function. So the product rule will be dy dx of the whole function will be, you have to differentiate first function first, multiply by the second function, plus differentiate the second function, multiply the first function. Critical part here could be to factor them and bring them together and simplify. That's a very critical part. So let's look into this particular thing once again here, how we should be doing it. So first part, of course, is the derivative. Amy, could you go through these steps and explain how the derivative of this function has been found?
Right. So to start off with, I would write the cube root of 6x squared minus 7 in exponential form, as you've done. So we got 6x squared minus 7 to the third, to the power of third. Now we find using the product rule formula. So you find the derivative of the first function, which is x squared. Yep, there. And then you multiply it by the cube root of 6x squared minus 7. Then you add the derivative of the second one, which is 6x squared minus 7 to the third, multiplied by x squared.
Yes.
So derivative of x squared is just 2x. Yep. Derivative of 6x squared minus 7 to the third is where you bring the third to the front, then you multiply it by 6x squared minus 7, then you do a third minus 1, which is minus 2/3, and then you times that by the derivative of the function in the brackets, which is 6x squared minus 7.
Correct.
Then you rewrite the first two parts of the 2x, add x squared to the third, 6x squared minus 7 to the minus 2/3, and then the derivative of 6x squared minus 7 is you do 6 times 2, which is 12. 12x to the power of 1 is just 12x. So that's that. And then you just make it a bit more neater. So you bring the 2x to the front, cube root of 6x squared minus 7. And then here, what you did was you did a third of 12x, which is 4x. And then you brought, 4x. And then you do 6x squared minus 7 to the minus 2/3.
Perfect.
So now here we have to factor out. So you find out the common, like the lowest common
Terms, right?
Terms. That's the word I was looking for. So we got 2x we can take out. And we can take out 6x squared minus 7 to the minus 2/3 because that's the lowest power.
Yes.
Then you multiply that by 6x squared minus 7, because when you multiply them out, you get cube root 6x squared minus 7.
Yes.
And then you add 2x squared because we need 4x cubed.
Correct.
Cool. And then you, what did you do?
Just simplify this portion. Nothing.
All right. Okay.
Yeah. And then we wrote it in the rational form. I should say the fraction form.
Yeah, you just brought because it's minus 2/3, you just brought it to the denominator.
Now, how do you find the critical points?
So the definition on the right-hand side says the critical points is where the derivative is 0 or does not exist. So we have to make the derivative that we just found equal to 0. Yeah.
The numerator.
The numerator, sorry. Yeah, you make that equal to 0. So when you do that, you get x equaling to plus or minus root 7 over 2.
Yes.
But don't stop there. Yeah.
Yes.
So because the other definition is or it does not exist. So when it means that, you have to make the denominator equal to 0.
Correct.
So you get x equaling plus or minus root 7 over 6.
Yes. So you get 3 critical points here. Perfect. So these are your 3 critical points, as you can see. Now what I have done in addition to that is we also sketched the graph of the derivative along with the graph of the function. So now, Amy, can you tell me, there are 2 graphs here. One is in green, the other one is in orange. Now, which graph is the graph of the function and why?
The graph of the function is the green one.
How do you know that?
So I was looking at, by looking at the orange one, which is the derivative, I can see there are 3 critical points.
Yeah,
1,
3 zeros.
2, 3.
Yes, yes.
So I just, knowing that I can see 3 zeros there, I chose that to be the
Perfect. That's a good idea. That's a good idea. So you went the other way. You found, we already calculated 3 critical points and you identified the graph which had these 3 zeros. And these 3 zeros are on the orange graph and therefore that becomes the derivative, correct? So the other graph is your graph of the function. So it's a smart way of getting through. And what you'll also notice is that, now, can you explain me one thing? We have orange graph as the derivative graph, where the zero, the leftmost zero, is at some point here, right? Now, at this particular point, which I'm pointing out, can you tell me it will lead to a local maximum or a local minimum on the main graph? What and why?
Sorry, what one are you pointing at?
This one, this 0.
So the question was on the f of x graph.
Are we going to have local maximum or local minimum at the very first left side 0?
Right. So how I would look at it is, so on the derivative one, the gradient is going from negative to positive.
Perfect.
So that means it's a local minimum.
Perfect. So
Oh,
now you got it. So the question really was the question which has not been answered by me. I wanted you to answer local minimum. So we have identified local minimum, right? So what you'll do actually speaking from here, that you have your, in fact, there are 5 critical points here. 0 plus minus square root 7 over 2 plus minus square root 7 over 6. There are 5 critical points here. Since we are also looking at the points which are leading to does not exist. Do you see that? So these
yeah,
vertical asymptotes are those other points which does not exist. So at these points also on the graph, we might have a local maximum or a minimum. Perfect. So the graph which I've drawn is the critical part is very, very small. I mean, width, the height is not much. So you cannot really see the maximum minimum. So the whole exercise for you now is that you have to make the table of interval and use this particular derivative which we have come across. And in that table, you have now 5 points. So you have 5 points which are going to divide the interval into 6 portions. Identify negative and positive regions for your gradient, and then you will exactly know which will correspond to maximum, which will correspond to minimum. And once you identify, plug in the value of x and find the value of y. So you will know the local maximum and local minimum points for this particular function. You get the idea,
makes sense. Yeah.
right? So that is your homework. So you have to do this question and continue with the solution to provide the exact points where the graph is going to have local maximum and local minimum, correct? The figure is going to help you keep you on track and also help you register how looking from the derivative graph we can figure out the answer, right? So
Yeah.
that's great. In addition to this, we have practice test questions. I'd like you to take a picture of these 3 questions now. Work them out.
Hmm.
Now, if you could read them and tell me what is your thinking and how can you solve these questions?
Right. So question 1.
Yes.
Find critical points on the graph of f of x equals 3x to the power of 5 minus 5x cubed.
Okay.
A. Find local maximum and minimum for the function f of x. B. Which critical points are not turning points on the graph of f of x?
Correct.
Okay.
Those could be point of inflection, correct? Do you understand how to do this question, right?
So find local maximum, minimum. So would I just find the derivative of the function,
Yes.
find the critical points,
Correct.
do the interval table, find the increasing and decreasing in that?
Perfect. Perfect. So if you get change in increasing, decreasing, you have a local minimum or maximum. If it doesn't change, then you don't have local maximum minimum, correct?
Yeah.
It would be a point of inflection. Now, please read question number 2.
Given f prime x equals x plus 3, x minus 3 whole cubed, A. Sketch the graph of f prime x. B. Identify local maximum and minimum on the graph of f of x. And C. Sketch the graph of f of x.
Correct.
Okay.
Right. It is exactly similar to our example number 2, where you have to sketch the graph and you know how to sketch the graph of this simple polynomial, correct? And then answer the questions, correct?
Yeah.
Since you have the function itself, it gives you a fairly good idea of even finding the accurate values. But even if you don't have accurate values for the graph of the function f of x, it is okay.
Okay.
Question number 3 for you.
Consider the function f of x equals 3x to the power of 4 plus ax cubed plus bx squared plus cx plus d. A. Find the constant a, b, c, and d if the graph has critical points at -2, -73, and 0, -9.
Correct.
B. Find the third point where the graph will have a horizontal tangent. C. Analyze the gradient to find local maximum and local minimum for the given function.
Correct. So that's a very big question for you. You are already given 2 points. And these 2 points are critical points. Find the constants A, B, C, and D if the graph has critical point at these values. Let me tell you one more added information. Horizontal tangent we have at these are the turning points. Okay. Now, when we talk about degree 4, the critical point could also be the one where we could have point of inflection, correct? Okay.
Mhm.
So, but anyway, whenever we say critical point, that means the derivative is 0. Is that clear to you?
Yeah.
So derivative you have to find, you have derivative 0. In the equation, we have to find 4 values, A, B, C, and D. But I have only given you 2 points. How do you find 4 values from these 2 points? Can you explain me that?
Wait, so the critical points are at x equals -2 and x equals 0.
Yeah.
Can you start by doing a quick rough sketch of the derivative using the zeros or no?
Yes,
Is
you
there
could.
not enough
You could.
information? Oh,
But
would that help? I don't
yes.
know.
Now, since I've given you 2 points, now important thing for you is that the points are on the graph. So if you plug in these 2 values, -2 for x and y value is -73, you get 2 equations from f of x graph. Is that clear to you?
Yeah.
Now, when you find the derivative, in the case of derivative, again you can plug in these 2 values because these points are on the derivative also,
Oh, yeah.
but with zeros,
Okay.
right? But with
Yeah.
zeros. These are zeros of your derivative. So when you say f prime x, and then you plug in these values, at x value of -2 and at x value of 0, you have a 0, right? So f prime
Okay.
x is 0. So you get 2 more equations. So
That
you have
makes sense.
4 equations and 4 unknowns, and therefore you can find all the 4 values. Does it make sense to you?
Oh, yeah.
So only x points for the derivative and both x and y points for the function can help you answer this particular question.
So critical points, they are points on both the function itself and the derivative, just that on the derivative, the critical points are the zeros.
Correct. So I should
Okay.
say the x values, at those x values, uh, the points are on the function. Let's be very clear. The critical
Yeah.
points are on the function. But at those x values, the derivative is 0.
Oh, okay.
Correct?
Yeah.
So
Yeah.
the
Yeah.
derivative. So when we find the derivative in that equation, you can plug in -2, but the derivative is 0, not -73. Okay,
Yeah.
0. Similarly, 0 and 0. So those will give you easy points to work with, B, A and B values, and then you come back to the function with A and B values and these points and work out C and D.
Mm.
So that is how you're going to work on this. It might take more than 10 minutes for sure. Okay.
Okay. Yeah.
So that's where we are going to end today's lesson. Now, this is a huge lesson, Amy, and
Mm.
because now you'll see this is our landmark. Once you complete this exercise, you're
Mm.
done. You're halfway through the calculus part because
Really?
yes,
Hey.
because you have understood the derivative, and now you have kind of understood how to apply it, right? You're
Okay.
right there to apply all the knowledge which you have gained so far. You've done it in I don't know, just in a week's time. That's great, actually. How do you feel about it? How confident you are?
Actually quite confident. I just feel like I need to review over a few old stuff. But the new stuff that you're teaching me, it's all fitting together and making sense. Like when I used to ask those questions, like, what is the point of all of this? Now it's actually making sense. Yeah,
Correct.
so it's good. And now I can sketch any graph because before I can graph a graph.
Yes, yes.
Yeah, before I could just sketch it because I just guessed the maximum and the minimum. Now I can actually find the precise value. So that's good.
Perfect. So, can you summarize today's lecture in 5 minutes?
Yeah, it's quite a long lecture. Yeah, so
Sure.
we learned about critical point being derivative equals 0 or does not exist. We learned stationary point being the first derivative has to equal 0. And we learned about local maximum and minimum. So that's where the gradient on a derivative graph, you have the gradient, if it's increasing to decreasing, you got your maximum. And if it's decreasing to increasing, you got your minimum. Then we learned about also you can have neither maximum or minimum. So that's when we use the cubic function as the example. And what else do we do? So this is a point that messed up with my head. Graphing. So you have the derivative graph, and you have to find the reverse. So you have to graph the function. So this is where you use the critical points as a starting point, plot the zeros, and work backwards. Yeah, so that would make sense. And finding critical points, what you do is you have the f of x function, you find the derivative of that, and then you would find your two values. So once you factor it, you would find the two values of x, or a value of x, and then you can use the interval table, which is where you have the negative on one side, the positive on the other. And if you factored it and there are like many terms to it, do it individually, and you don't have to find the actual value, just find if it's positive, negative, multiply them and find the derivative. If it's positive, increasing, negative, decreasing, and that's how you'll find your minimum and maximum values. Once you find those points, you just sub it into the original f of x equation and you get your actual points.
Correct.
And that's it, I think.
That's great.
Just practice.
So, okay, all the best. Tomorrow again, we'll be back with the same exercise. I'll see how you have performed on this. I'll also share with you some more videos which can help you answer these questions and learn a bit more. So we'll stay at this place for another day, and then move on to next unit on rate of change, okay? Which will explore more about the second derivative of the derivative, and look into the applications of velocity and acceleration.
Okay, cool.
Great.
Thank you so much, sir. Really appreciate it.
Have a great day. Bye.
You too.